Okay, already on to our second lecture in quantum mechanics. I had both of you, Trace decided not to take the class, just in case you're wondering. Both of you asked me about this homework problem, and as I think I might have mentioned to both of you, it's not easy and it's not super relevant to quantum mechanics, but it is relevant in two ways. Number one is the origins of quantum mechanics start with studying black body radiation. And this gets you thinking about how you solve problems. So it's kind of a doozy. It has almost everything you need here. I just looked at my solution, Chad, and realized, oh, that last step was actually really super obvious if I actually think about it, you know. But there's that think about it part. So I know that that Erin said she already has this completely done. How far did you get, Chad?
Maybe, I don't know.
I haven't done it.
Okay. Okay, so let's just look at the problem so that we're clear on it and know what our pathway is. So we have a black body radiator here. Oh, really?
Where do you upload these lectures to? Just the Google?
I haven't yet. The stuff with me talking will be uploaded to YouTube, and I probably won't get that set up until Thursday because today is not a day when I have a free moment.
You have the lecture from yesterday on Moodle. I thought maybe it's from last year.
It's probably from last year.
Okay.
I mean, there's going to be a lot of similarity, and
right.
You can watch all of last year's lectures on YouTube. But it's probably not until Thursday they'll actually have it available for this year's stuff. I'm fundamentally doing the same lectures, but every year it's different. Okay, let's start with what a black body is. A black body is something that gives off radiation because it's hot. The hotter it is, the more radiation it gives off. Why do we call them black bodies? Because black is the ideal radiator. Something that is black will absorb perfectly and emit perfectly. And so a way that we often will simulate a black body, having something like oven or some hot with a hole in it. And that cavity then will behave like a black body with an emissivity of 1. That is like a perfect black body. So that's what this problem is actually dealing with. It's not saying we have a real black body. It's saying we have a cavity. The cavity behaves like a perfect black body because, of course, anything that hits this hole goes through. And that's what defines a perfect black body, the radiation going in and out. Inside, you have something that's hot and in equilibrium. So that's what the simulation is. And so this says to assume isotropic radiation, which means that the radiation is going out in all directions equally, except for one thing, which is given here at the very beginning. No, not the very beginning here, that it's isotropic, but if you look from a different angle, it looks like a smaller hole, right? If I look at it from this angle, it looks like a small hole. If I tip it like that, it looks like a bigger hole. And so that's why we have this term that I circled there. That's the effective size of the hole seen from a different location. And so what we need to do then is to calculate du, the amount of energy per unit volume, will be equal to the rate at which it's being emitted times that effective area, which is dA cosine theta, over 4 pi r squared. As I explained to Chad, he didn't ask, I just explained. The 4 pi r squared is because we're assuming that the radiation is spreading out over a spherical shell. The surface area of a sphere is 4 pi r squared. And so as it gets farther away, the same energy is spread out over a bigger area by that factor of 4 pi r squared. So we have that and then times dV. That's what this statement here is saying. The energy contained in the volume element dV is dV multiplied by the energy density. So now I have du. I need to integrate this to find u. and you'll integrate over theta, phi, and x, where x is going from 0 to c delta t. And then the final step, the one I couldn't remember when I was talking to you, was to Chad, is that we want to find the energy density, and the energy density is I'm just going to write energy density because I'm going is equal to U over the area and time. So that would be over delta T dA.
I thought that was the emissive power.
You're right, emissive power. See, you are correct.
But I'm still not certain why it's over dA.
Actually, it's intensity. That's why. Intensity is power per unit area.
Okay, so when you, I think in the beginning you said prove that the, energy density between energy density and emissive power, did you really mean emissive intensity?
I copied this from a different textbook, so that would be, did he mean, you're right, that it's definitely intensity.
Okay.
So that was the final step there. You need to take the U and divide it by delta T dA. So this problem here, like I said, it's not a quantum physics problem per se, but it just is something to get you thinking. So now I'm going to go on to quantum physics for real.
Could you explain really quick why
Sure.
you integrate from 0 to pi in the...
It's actually 0 to pi over 2.
Yeah, for the theta. But why for phi do you integrate from 0 to pi?
0 to 2 pi.
I did that. Oh, God.
Okay, so phi, the integration limits. The picture shows that theta is the altitude angle. And so theta 0 is straight overhead, and theta being pi over 2 is in the horizontal plane.
Yeah.
So you can't go deeper than the horizontal plane. So that's why that's 0 to pi over 2. And then the phi is the azimuthal angle. So you start here and you can go all the way around in full circle. So that's why it goes 0 to 2 pi.
Then in my answer, I end up getting 2e over c instead of 4e over c. So there must be some other place where...
Yeah, I would have to go through the actual integration to
I'll have you look at
to look at that. Yeah. All right, going to the lecture material. See where I was thinking. We are going to not introduce the Schrodinger equation per se today, but we're going to talk about the basis of the math of quantum mechanics. And so this is the Schrodinger equation. This is the fundamental equation that we use to get a wave function. So here is a terminology thing that never stuck with me until I started teaching and realized, at some point I'm going to have to get this straight. We have the terms wave equation and wave function. The wave equation, this thing right here, is an equation that we use to find the function. So we use this to find what this this function is. So psi is the wave function, and the wave equation is this equation that we use to find the wave function. Now I just said psi so trivially. In quantum mechanics, we do say psi very trivially. This here is a capital psi. We will also see the lowercase psi, which is written more like that. And we will say, we'll have a bunch of these functions that we combine to make this function. And so we'll make the lowercase for the individual ones and the capital for the complete one. So when I say psi, I mean the wave function. Wave function is the function that ultimately carries all of the information about the particle. Now, something I kind of alluded to in the class yesterday is the realm of quantum mechanics. It is sometimes said that relativity is the physics of the very fast, which is somewhat true, very fast or very massive, because relativity also is going to have, mass affects space-time continuum. Then they say that quantum mechanics is the physics of the small, which once again is relatively true. Quantum mechanics does not require something small. I said in class yesterday, we could use quantum mechanics to describe you. The thing is, it's super complicated. It's not going to give you any different result than classical physics. So what's the point? We could do it. It works for large things. It works for everything. We have this thing we call the correspondence principle that says that our physics, we have classical physics, which is the physics of every day. Also, the physics of everything before 1905. We have classical physics, and then we have the specialized physics, the quantum mechanics or the relativity. And in the region of overlap, the region where you have classical systems, like talking about you and me or a ball, they have to give you the same result or you have a problem. So that's our correspondence principle there. So this Greek letter psi, a meaning of it using Born's statistical interpretation is the probability density. And already we get to a term that on the face of it doesn't make sense. I mean, how do you have a density of probability? It doesn't really compute. But here is an example, obviously from physics, to get us to where this really comes from. If we take light, the ultimate thing we see in light is the intensity of the light, how bright it is. And how bright the light is proportional to the square of the amplitude of the electric field. Right? You have an electromagnetic wave for light. And so you have, I say the amplitude, I should have said displacement. The size of the wave, the bigger the electric field, the brighter it's going to be, and the brightness is proportional to the square of how strong the electric field is. So that makes good sense. When you do a diffraction grating, you have light that goes through the slits and it makes a pattern of bright, dark. You can go each place and say, okay, it's this bright here, so the average, and now we can't say amplitude because we're talking about the average over time, is this big. But using the particle wave duality, we can also say that we have no photons hitting a place where there's no light, and we have a lot of photons hitting where it's bright. And so we can take that same information using the amplitude of the wave and say, well, the amplitude squared gives me the intensity, which is proportional to the probability of the photon hitting. The higher the amplitude squared, the higher the probability of the photon hitting that spot. And so with understanding of the wave-particle duality with light, and this is, I believe, where Schrodinger was going when he came up with this equation, we should be able to find something that is a function, like the electric field function for light, that gives us the probability of finding the particle, like the electric field function for light gives us the probability of finding the photon. But you have to square the electric field function to actually find the probability. It's not the amplitude or the displacement or amplitude. It's the square of that. And we have the same thing here. So that's what we mean with probability density. If we take that wave function and we take the magnitude squared, that will give us the probability. Question?
So does that probability density have to do then with the idea of a matter wave? So the particles of light traveling as a wave together and forming?
That wave function psi is describing the quote matter wave.
Okay.
So yeah, I never use that terminology, but that is what it is. So you take mathematical discussion here. How do you read that? That's just asking how you read the math.
Absolute value of the function of psi in terms of x and time squared.
Okay, that's how most of us would read it, times dx.
Okay.
That's how most of us would read it. In quantum mechanics, we say it a different way. It comes out to mean the same thing. Absolute value is taking, the magnitude, right? But psi is going to be complex. Complex means it has real parts and imaginary parts, and difficult as well, but mathematically, real parts and imaginary parts. And so to find the magnitude if something has real and imaginary parts, we actually think of things like this. Here's the real part. Here's the imaginary part. And so I have something that has this much real and this much imaginary. How do I find the resultant that I get with those perpendicular real and imaginary? What would we call the simple equation that we use to find that? To find the length of this. Like if we know this is A and this is B, how would we find this? The what? The Pythagorean theorem. And so that's what we do with these complex things. We essentially use the Pythagorean theorem. We take the real part squared plus the imaginary part squared. And then we take the square root if we want to find the magnitude. Here we want the square of the magnitude so we don't have to worry about square rooting. And so that's what it means when we have this absolute value squared. We're going to find the square of that magnitude. Now mathematically, the way we do this is we take, okay, let's say psi is equal to A plus IB. So you can right away say then the magnitude of psi should be square root of A squared plus B squared, right? And there's our answer. That little star means complex conjugate. And complex conjugate means you change the sign of any imaginary value. And this thing here is pronounced psi mod squared, right? You read it the way any normal human would read that who's had math up to a reasonable level, absolute value of psi squared. But we call it psi mod squared, and what that means is we're going to take psi and multiply it by psi star. And if you do that, that would be equal to A plus IB times A minus IB, which would be A squared. You'd have plus AIB minus AIB. I'll write it down. And then minus I squared B squared. The middle terms are going to add to 0 because they're exactly the same, but one's positive, one's negative. And what's I squared? Negative 1. So A squared minus negative 1, which means plus, B squared. So that gives you A squared plus B squared in the end. And now you're probably saying, why didn't we just say A squared plus B squared? Why do we go through all this foolishness? The reason is because our wave functions are usually much more complicated than A plus IB. And so using this mechanism of doing psi times psi star, or psi mod squared, is the quickest way to find that probability density. Yes?
Sorry, so
or probability, excuse me.
The A plus IB was just an example of a wave function that we could have?
It's not a real one. It's an example of a complex value. I was going much simpler than what we're going to have for a wave function. A plus IB would not be a legit wave function in any way, shape, or form.
Oh, what's the 44? Or are those two sides?
Yes, those are two sides. Sorry. Yes. I was like, 44? Yes, that's psi times psi star. Now, coming back to the box in green. So the probability of being between x and x plus dx is psi mod squared dx. Remember last class period I was talking about the probability of being right at 400 not the probability, the amount of light at exactly 410 nanometers, and it's 0. But if we have a small width, then we have a realistic value. That's the same idea here. The probability of being in this range is this function times the range. So this together is the probability of being in that range. And if I want to have a bigger range, dx, remember, is infinitesimal. If I want a finite range, then I'm going to have to add this up, going from the beginning of my window to the end of my window. And since psi is generally a continuous function, how do I add up continuous function over a window? Okay, since this is a continuous function, if I have a window like from x equals a to x equals b, how do I add this up through that window? I have to add up all the little infinitesimal pieces. We do what?
It just seems really, seems like there should be a better way than adding everything.
There is, and that's why Newton invented it. The integral. The integral is how we add them up. Yeah, it seems like there's got to be a better way. That's what Newton said. So if I want to find the probability of being between A and B, that's going to be the integral of psi mod squared dx from x equals A to x equals B. So there's already some interpretation now of what this wave function actually means. It has some usefulness. It's going to turn out it has a whole lot more usefulness, but that's a beginning part. So you have questions about what we have in the wave function so far?
So you said that was kind of a wave function?
Well, no. This would never be the wave function. This was just an example of a complex value.
Okay. And then in the green box, that's not a wave.
Well, this is a calculation. This is the probability of being in this little window. But the whole thing is necessary for the probability of being in the window, not just this part.
You have psi is equal to a squared plus b squared, but
Well, where do I have that?
Okay, so psi times psi mod is equal
Yes.
to a squared plus b
Yeah.
squared. But psi by itself is equal to the square root of a squared plus b squared from your imaginary and real.
Psi by itself would be something like this, a complex value.
Okay, where does the Pythagorean theorem piece come into?
So the Pythagorean theorem was, how would we find the magnitude of something that has two components that are right angles to each other? Because when we talk about the complex plane, we have the real part and the complex part is perpendicular to each other. And so that was just for understanding how a squared plus b squared should be the magnitude.
Of psi squared, right?
Well, yes, it's the magnitude of psi squared. You square root and you have the magnitude of psi. All right. Philosophical interpretations. Yes, quantum mechanics, it's a whole lot of thinking. And so there are philosophical ramifications. And so here are three different possible interpretations of what quantum physics really means. And we have the one that's called the realist, Einstein. Nobody calls Einstein a dummy. We have the orthodox or Bohr interpretation. That's the one that is generally accepted. And then we have the agnostic, which is probably the easy way out. So the question, suppose a particle is measured to be at point C. So at some instant in time, I measure and I say, this Van de Graaff generator is right here. Where was it immediately before the measurement? Now, when I was in your shoes, I had the very, very Einsteinian realistic interpretation. When we talked about the uncertainty relation, the uncertainty relation says that you can not at the same time know precisely the position and the speed, but you can arbitrarily know one. So you could, for instance, know exactly the position, but have no idea the speed. And I said to myself, I'm not as dumb as they think I am. If I can determine exactly the position now, and then I wait a millisecond, and I measured exactly the position then I can calculate the average speed in between, and that's a small enough, time gap that I can say I know both the speed and the position quite accurately. Well, that's not the way, that's the realistic interpretation. That's the way that Einstein viewed it. You may or may not be familiar with Einstein's quote. It says that I don't believe that God plays dice with the universe. Have you heard that quote? Now, Einstein, depending on the day of the week and who asked him, may or may not have believed in a God. I think generally he's considered agnostic, but sometimes he talks about, nature without God is useless and things like that. So maybe he believed in God. But in this quote, I'm pretty confident I know what he's talking about. He really was fighting against that orthodox view. The orthodox view says that nature is itself probabilistic, that we cannot take the information we have right now and accurately calculate what's going to happen a split second from now. It's probabilistic. We can calculate the probabilities of different outcomes, but we can't say exactly what's going to happen. And Einstein fought against that. He said, no, if we have precise enough information, we should be able to precisely predict what's going to happen. And the problem is the precision of our data. The orthodox view is that nature is, in fact, probabilistic, that there's a randomness in nature. We can only calculate what the probabilities are of things happening. And so, the realist view is, well, a split second before I measured it was right here or maybe just getting to right here. But the orthodox view says that before I made the measurement, my particle was spread out all over the place. It was not localized. Now, how weird is that? When I look at you, you're localized. Right there is Aaron. Right there is Chad. Right there is Nathan. But the orthodox view says that's not so. You are spread all over the place. It's only when I look at you and make the measurement that I force you to collapse to one location. And so I look away and you spread out again, and I look and I force you to be somewhere. That's kind of weird to think about, isn't it?
Yeah, isn't that explained further that things like a measurement isn't just one person, it's like everyone observing things, so we're not bouncing all over the place because not only you're looking at me as measuring where I am, but so is Aaron, so am I, so is Nathan.
So the chairs, things that we're touching are.
Yeah. Or you're observing, I guess would be a different word for measurement.
Or
is that something else?
That would be something else. Because for things of our size, the wave function is going, there's still a wave function for it, but it's very sharp. It's like the wave function for the particles in this room. You have lots of different temperatures that are available, lots of different pressures, lots of different positions, lots of them. And so when you do the statistics, you find that the probability for this temperature, pressure, volume is very high. And if you change the pressure just an iota, it drops to virtually zero. Still possible, but it drops to virtually zero. And so it's possible that all the molecules could be in a corner and we suffocate. But the probability is so low, no one worries about it. That's what the second law of thermodynamics is. Second law of thermodynamics, that every natural process results in an increase in entropy. It simply says that every natural process is going to go to a more likely outcome. It's not going to go to a less likely outcome. If you start here, it's not going to go somewhere unlikely. It's going to go somewhere more likely. And so it's the same type of statistics that says we see you as right there. Even when I look away, you're there actually, because the spread in your wave function is so small, I couldn't tell the deviation. There really is some fuzz to you that no one can tell. That's what the quantum physics is. So when I look at you, yeah, it does force you into one position. And I look away, I look back, force you into a position, but there's no way I can differentiate between those.
What about attractions, like the particle had a magnetic or electrical dipole and was attracted to the measurement device or something that was nearby point C? Mm-hmm. Isn't there a high probability such a high probability that the particle is right there attracted to that thing rather than being spread out everywhere?
You can make situations where you make the probability very high for one place, in which case you don't think about spreading out again. So yes.
So like a human being.
Yeah. I mean that would be for a different reason.
Yeah, but still kind of the same conclusion that you make.
Okay, so the Bohr, when we talk about particle in the box, we'll understand this, I think, better. But it's important to have some understanding of the underlying thoughts, because quantum mechanics is not an intuitive thing. And the agnostic view is, what's the point of asking? That's almost like, Heisenberg with remember the very last two sentences of the lecture yesterday. Heisenberg said, we have no way of knowing what the path of the electron is as it is in it's in an atom. So let's not worry about it. Let's just move on to the things that we can observe. Okay. I've already actually talked about that more than I care to. Let's go to some examples. We're going to do what really are quantum mechanics calculations, but they don't look like quantum mechanics calculations. And I'm using the numbers and the examples from the textbook here. So if you look in the textbook, it has exactly what we're doing here. So things we use in quantum physics a lot are statistics like, determine the probability. So let's look at these numbers. What's the This is just a distribution of people's ages. Based on this distribution, what is the probability of a single person that you grab one person from this group of people? Probably that person is 14 years old.
100%.
You chose one person randomly from the group.
I think I misunderstood.
Okay, you have 14. If you add these up, this comes to 14 for this column.
Oh, I thought you were saying you had 4.
Yeah, you're saying if I grab a 14-year-old, what's the probability they're 14 years old? Yeah. So you have these 14 people. They're in a room, and you randomly grab one and say, "How old are you?" What's the probability that their age is 14? One 14th. And for 15, likewise 1/14. What's the probability for 16, just to make sure we're following along? Okay, so here's our probabilities for each one. That wasn't very difficult. What's the most probable age? 25. How do you come up with 25? Because you just look at the probabilities. That's the biggest probability. So most probable, once again, not a difficult idea. Now to something that is a little more quantum physics-y. What's the median age? What does the term median mean? The middle one. So if we look here, we have 6 people that are, let's see.
22.
Yeah. I don't know how I did my math, buddy. 7. Yeah. There are 7 people that are 22 and younger, and 7 people that are 24 and older. So the textbook says 23. Because at 23, half the people are older, half the people are younger. If it comes between values, you just choose value halfway between. So the median here would be 23. So the most probable 25, the median 23. How many people are going to be 23? 0, right? So just because it's the median doesn't mean it exists. Okay, what about the average age, also known as the mean, or in quantum physics, the expectation value? We'll use the word expectation value a lot. And the word expectation value means if I took a statistically significant number of measurements and I take the average of those, what do I get? So in other words, it is the average. So what's the average of these?
Once you multiply the probability times the age.
Who's going to write here? That wouldn't work. Okay, so the median, or the average, A-V-E, wow, I can't write average. We indicate the average or expectation value by putting it inside of the greater than less than sign. And we calculate it by taking, this is what I believe I heard Chad to say, we're going to sum each age measurement multiplied by the probability of being at that age. So sum over all j's. And so in this case, I take 14 times 1 over 14 plus 15 times 1 over 14 plus 16 times 3 over 14. Add those all up, and I get the average. Simple enough? Just for grins, I'm going to look to see what that value is. The value turns out to be 294 over 14, which is 21. Just because the book has the same number, that's why I'm using the textbook's number. So that's kind of useful. How many people are 21? None. So your expectation value doesn't necessarily exist. And we're going to see some clear examples where that's the case, where the expectation value can't exist. Now we have a few more things. The average of the squares. Well, if this is how you find the average, how would you find the average of the squares? So just using, that's a square, by the way, just using the same thing we did. All this changes, we have age squared. So how am I going to alter the right side of the equal sign? Are you guys familiar with this? Okay, just making sure. And the J means summing over all J's. That's right. So in this case, I would have 14 squared times 1 over 14 plus 15 squared times 1 over 14 plus etc. And once again, see if the textbook actually gives me the answer for that. It doesn't. You think they would give me the answer for that, but they didn't. By the way, on the next homework assignment, the one that's going to be due next week, you're going to be doing all of these calculations with a set of numbers. I strongly recommend you do a spreadsheet. Right, because you're doing all these calculations. They're very simple to do on a spreadsheet. If you don't know how to do it on a spreadsheet, come see me. Right, I'll help you get it going. But it's painful to do this all by hand. So this is how we would get the average of the squared age. Now, the average of the squared age is not the same as the square of the average. In general physics, I just use this as my explanation. Let's take 1, 2, and 3. What's the average of 1, 2, and 3?
6 divided by 2.
6 divided by 3. Which is, 2. Yeah, I think you just jumped to the answer. 6 divided by 3 is 2. So the average is AVG is equal to 2. If I square it, and I take the average of the square, that's going to be 14 divided by 3. I think it's clear to see that 2 squared is not equal to 14 over 3. And in fact, if we take these, 14 over 3 is going to be a little bit more If it was 12 over 3, it would have been 4. So 14 over 3 is a little bit more than 4. It's 4.66 repeating. And so the average of the squares is always going to be bigger than the square of the average. Or it could be equal in the extreme case. But nevertheless. Why do I do that? Because that brings us to the last thing here, the standard deviation. The standard deviation, and the textbook goes through a good explanation of why we use this. You can have two distributions. If you look at your textbook, I will. Here's a graph. I'll just walk up close to you guys. Here's a graph showing the distribution that we've been working with. And so with this distribution, we get a certain average, right? And then here's two other, now these are not the same data, two different distributions of data that have the same average. But they're not equivalent distributions. One of them is more spread out, one of them is not. And so we want something that will help us to understand that spread in the value.
So you're giving more weight to all of those values that aren't in the middle by taking the average of the squares?
Well, I haven't gotten to what we're going to do. What we're going to do is the standard deviation.
Okay.
But the justification for why we do the standard deviation. Okay. Might as well give you the answers you're asking about.
Well, I was wondering if that's why we do the average of the squares, but you do the average of the
Yeah, we do the average of the squares to get to the standard deviation. It will have its own value to us on its own right, but right now I'm doing it to get to standard deviation. So how do we differentiate these two distributions? If we, in quantum physics, we talk about the expectation value. If we only talk about the expectation value, we can have two very different systems give us the same expectation value and somehow think that they're the same. So one thing that you could do is calculate the actual deviation between the mean and each data point. That is, you take the mean, the standard, or the expectation value, and you take the value for each one, and you just say, well, the deviation minus, that's a minus sign, is the age of, the deviation for person J is their age minus the expectation value or the mean. But the usefulness of that is just about the same as the usefulness of what's the average voltage coming out of the wall. The voltage coming out of the wall is sinusoidal going between plus 170 and minus 170 volts. What's the average? 0. If I take the average of the deviations, it's going to come up to 0 because I have the individual values minus the mean. If I take the average of this, I'll have the average of the individual values minus the average of the individual values is 0. So finding the average of this deviation is fairly useless. And so instead of finding the average of this, what we do is we find the average of the deviation squared. So we'll find the average of that. And then for the standard deviation, you square root it. This here, by the way, is called the variance. Well, it's called the variance when you take the average of it. So how do I indicate the average of it? Well, nomenclature. How I indicate nomenclature is putting those things, because that's our way of showing that we've done the average. Now, if you look at the top of page 9 in the textbook, he does a very quick little mathematical breakdown to show that this here turns out to be equal to, and I'm not going to go through the work because it actually is really self-explanatory if you look at page 9, but this is equal to that. The average of the squares minus the square of the averages is equal to the variance. So you should look at, like I said, the top of page 9, just to look through the math steps. And it is pretty straightforward. And so when we want to find the standard deviation is the square root of that variance, which means it's equal to the square root yes.
That's where I have to go.
It's in my okay. We are only 3 minutes in the class, but so we're going to be doing calculations with that. Like I said, for the next homework assignment, you're going to have a bunch of numbers, and you have to go through and do these different calculations, find the variance, find the standard deviation, so you can show that you have the statistical background that we're using in quantum physics. So we've gone through all of these statistical calculations. Any questions about the statistics? What you've seen so far today about quantum mechanics is that we have this wave function that comes from a wave equation. The wave function gives us probabilities. So in all the stuff we've been doing, I had a probability here. If I'm doing quantum mechanics, this probability is going to be psi mod squared, d whatever. And so I'm just going to be putting those psi mod squareds where we did a simple calculation here for what the probability is. So what we're doing here is directly applicable to what we're doing in quantum mechanics. And now we see that quantum mechanics is based on probabilities. It's not deterministic. You cannot say, I have an electron here, and so next time I check, it's going to be here. You simply can't say that. You have an electron here, probabilities. Let's take this to something that should be real to you guys. You guys have studied chemistry. You know about s orbitals, p orbitals, and so on, right? What does it mean if you are in an s orbital?
Yeah, it's what lies within that orbital.
It can vary within the cloud of electrons.
Yeah.
Okay. It tells you that you have a spherically symmetric probability for finding that electron. And so that spherical shape is just telling you it's a spherically symmetric probability function.
Okay.
And you generally have an exterior that you see, and you don't see the interior. If you go to Orbitron, you can see the full thing. But there's a probability of it being, in this region, so on. And the probability function, if you go horizontally, just looking at radius, the probability function is going something like this.
Okay.
And so what you're seeing is somebody just said, let's cut it off at 90% probability and make what the shape looks like for the farthest out at 90% probabilities. And so the s orbital is spherical. And if you have a p orbital, of course, we look at it as a dumbbell shape. What that's saying is that it's no longer spherically symmetric probability for the locations of the electrons. When I was in high school, I took that board. I honestly, I got to college and I still was like, I don't know why the teacher's going on about this. Okay, can't do that well. Somebody's calling me now. Whoops, my accent. No, so this is time to quit class. I'm sorry. I try to keep it up. I was talking about the p orbital, right?
Yeah.
Okay, so what the p orbital is telling us is that we have a non-spherically symmetric probability of where we're going to find the electron. And when I was in high school, I did not understand the difference between the Bohr model and the standard model. And our teacher's like, it's different. Well, how is it different? We still, I looked at the s orbital. And I said, what? Just what? There's the thing. But that's not what's going on. It's not doing a circle. We don't know what path it's doing. The electron could be stationary for all we know. In fact, the angular momentum in an s orbital is 0, right? So, I mean, it could be stationary. It's not. It's not stationary because when you measure electron position, you can find different locations. But, who knows what it's doing? All we say is the electron is delocalized in that orbital we're seeing. And so the orbitals are depictions of what we're going to get at the end of this class. When we're done with this class, we will have a map to describe those orbitals. That is our end goal, our end game in this class.
Through all of them, SPDF.
Yeah. And of course, our math will give us all of these equations. Good Lord, won't be drawing orbitals or anything like that based on the equations.
We already did that.
All right. Have